Now, our topic is acid properties in DBMS. The full form of acid is A stands for atomicity, C stands for consistency, I stands for isolation, and D stands for durability. These acid properties in DBMS are commonly recognized as fundamental principles of DBMS. All these four properties of DBMS collectively ensure that all the operations in the database are performed reliably and that the data remains consistent even in the presence of failures or concurrent transactions. It means that when many operations are being performed on the database, these acid properties ensure that database remains consistent even in the presence of failures. Failures means system failure, power failure, internet failure. Now we will discuss each of these properties one by one, and also we will try to understand each and every property with the help of real life example, so that we can not only understand the concept but also its usage in real life. So let us start the first. Atomicity. Atomicity means either all or none. It means that either a transaction should be performed in full or all the operations of the transaction are reverted back. Now let us read. Atomicity is one of the acid properties in DBMS. Atomicity ensures that a transaction is treated as a single indivisible unit of work. Atomicity means that either all the operations within a transaction are completed successfully or the entire transaction is rolled back to its original state if any part of the transaction fails. We try to understand the same with the help of an example. Suppose you go to an ATM machine to withdraw money. You have to perform many steps. First, insert the card. Then you may be asked to fill your preferred language. You may be asked about your PIN. Then you may be asked what you want to perform on the ATM machine, whether you want to balance your check or you want to withdraw amount. Then after entering the amount, you may be asked how many amount you want to withdraw. That is, there are many operations within the single transaction. Either you want to withdraw money from the ATM machines or you want to check your balance in your account. So these are all the operations which are involved in a single transaction. So when there is, suppose, internet failure or power failure, then at whatever step you are, that is either you are entering your PIN or after that you may be entering the account amount which you want to withdraw from the ATM machine. At any step, if there is failure of internet facility or power failure, the system will revert back to its original state. That is, you will have to perform all the operations again. We will understand this concept in more detail with the help of further examples. This property prevents partial updates. This property is crucial for maintaining the consistency and integrity of the data in the database. Now we understand this concept of atomicity with the help of few examples. Suppose you are having an account in ABC Bank. This is you, and you want to send money to your friend B. Suppose there are $100 which are present in your account. That is the balance which is at present in your account. Here, friend is having $150 in his account. Now you want to send, say, $20 to your friend which is having account in the same bank. So now what will be done by the DBMS? It will deduct $20 from your account, and this $20 will go to the account of your friend, and its balance will increase to $170. So if there is a system problem or system crash or internet failure or power failure at any of these steps, this is the whole transaction, and these are the two sub transactions or two operations of the single transaction. Now if suppose while 20 is being $20 is being deducted from your account, it may happen that power failure may occur at this stage, or it may be possible that while your account has been debited, but when the transaction or operation was going on of crediting the amount to your friend's account, at this step there was failure of power failure or internet failure, and the account of your friend was not credited with $20. Then the atomicity property of DBMS ensures that all this transaction is reverted back. That is, your account balance will be again shown as $100, and your friend's account will again have the balance of $150. That is, no credit, no debit. The debit which was performed on your account will be reverted back, and you will again have the original balance of $100. Now we take another example of airline reservation system. When you book your ticket for a flight, then this transaction involves some steps, that is reserving tickets. That is, you open the online site, you reserve the seat if the same is available, reservation of seat. After, when you click that I want this seat and the seat is available on the site, then the site will ask you to make payment. Then this payment will be deducted from your account, and then the system will, the website which you have approached will update the balance. Suppose here the balance of tickets in their online site was showing as only 50 seats are balanced, and you book only 2 seats. Then the DBMS system will ensure that 48 seats are balanced shown on the site. All this happens only because of the atomicity property. That is, if there is, suppose while the system is going to reserve 1 seat, 2 seats for you, and you are making payment, and at this step, suppose when you are making payment, suppose there is some internet problem at your end and you are unable to make the payment, or you have not been able, or your bank has not been able to make the payment to the concerned website, then the DBMS system will ensure that the seat which was being allocated to you is reverted back to 50. It may be also possible that when the system was going to update the seats, it may be having some problem. Then if at any step, that is either at the step of reserving seats or making or deduction of payment or updating the balance seats, if there is any problem, the whole transaction is reverted back. Let us read. When a customer books a flight, the system has to take many steps. such as reserving seats is if available, deducting payment from customer's account, and updating the remaining available seats. If all the three steps, that is reserving seats, deducting payment, and updating availability, are completed successfully, the DBMS ensures that the changes made by the transaction are saved in the database. If any step within the transaction, all these steps are represent the single transaction, encounters a problem or an error such as the system crash or power failure, the DBMS ensures that the entire transaction is rolled back, meaning that any changes made by the transaction are undone. Next is ATM withdrawal. When you approach an ATM machine for withdrawing cash, first of all, you will insert card, then the system will ask you your PIN number, and when you select the option that you want to withdraw the cash, the ATM machine or the system of the bank will check whether there is sufficient balance in your account, so that it may be able to cover the withdrawal amount. Suppose you may be having $10,000 in your account and you want to withdraw, suppose, $11,000. The system will say that you are not having the sufficient balance, so it may decline the transaction, or it may ask you to revise the option. If you are having, say, if you want to withdraw only only $5,000, the system will allow you. And after deducting the withdrawal amount from the account, your account balance is updated. That is, when you say that I want to withdraw this much amount from my account, the ATM machine will first deduct the amount, it will update the balance in its record, and after that it will dispense cash. If at any of these steps there is system crash, power failure, or internet failure, the DBMS system or the atomicity property of the DBMS will ensure that all the steps all the operations which have been performed in this transaction are reverted back. That is, you will be placed in the first position, that is from wherever you started. Atomicity ensures that if any part of the transaction fails due to a technical issue, network problem, or any other error, the entire transaction is rolled back. Now we learn about or understand the second property of DBMS, and this is the consistency property of DBMS. It is also one of the important acid properties. What is the meaning of consistency? Consistency means correctness of the database. It means that the database should be consistent before and after the transaction. We understand the same with the help of an example. Suppose you want to send money to your friend. You want to send $20, and after sending the amount to your friend, your account balance should be, we will write here. Suppose you are having $100. You want to send $20 and the balance in your account should be $80. On the other hand, if your friend is having $150 and you send him $20, the balance should be $170. That is, here the database is correct. That is, here 20 has been debited and here $20 have been made credit. That is, overall the position is the same. That is, If we sum up the balance of both these accounts, it means $250. And after the transaction, if we sum up the balance of both these accounts, it also means $250. That is, there is no consistency in the database. That is, it means that the system has not credited $10 or 15 or 30 or $50 to the account of your friend. It has debited the exact amount which was deducted from your account, and the credit of the same amount has been given to other person. Within the database schema, there exist integrity constraints and rules. These rules are essential for maintaining data accuracy. How this happens? How this consistency happens? For this, there are integrity rules or certain regulations which the DBMS system follows. These regulations are enforced consistently during the execution of the transactions. That is, at the each and every step of the transaction, these rules or constraints have to be followed by the system itself. We need not to worry about the technical aspects of DBMS. The DBMS system itself takes care of all these technicalities. This consistency property prevents any breach of these rules. These breaches could result in inconsistent database state. If there has not been the consistency property of DBMS, then it might have been possible that incorrect amount might have been credited to another person. Now we will try to understand this property of DBMS with the help of an example. We take the example of hotel. Suppose you have visited New York many a times, and one of the hotels is your preferred, say it is ABC Hotel. Suppose there are two persons or two customers, A and B, which want to book, say, room number 1. So the DBMS system will ensure that the two customers are not allotted the same room, or it may be possible that there is some renovation going on or in the hotel, or only a few rooms are there available for occupancy. The DBMS system will ensure that no room is allotted to more than one customer. That is, one room, one customer. And in case if it happens that is same room is allotted to two different customers, what will happen? There will be naturally customer dissatisfaction or dispute with the hotel, and it will earn a bad image for the hotel. Let us read what is written. Hotel room reservation. When customers make reservation for hotel rooms online, the DBMS ensures that no two customers are assigned the same room for the same dates. That is, both the customers want to book a room for the same date. Irrespective, we can say that room number 1 is not selected. They want to book any deluxe room. So the system will ensure that a particular deluxe room is allotted to only one customer and for a specific date. The database enforces constraints to prevent double bookings, maintaining consistency in room assignments. Next is the e-commerce orders. Suppose you are visiting Amazon site and want to purchase something. You place an order to purchase a PC. You have placed the order. Now, the DBMS system will ensure that suppose there are 100 PCs balance which are being shown on Amazon site. When you have placed the order, the DBMS system will ensure that when you have placed the order for one PC, the DBMS system will ensure that the balance inventory in their site or in their inventory should be 99. Let us read. When customers place orders online, the DBMS ensures that the items purchased by the customer is deducted from the online inventory and the quantity of products in the inventory matches the actual number of items physically available. It means that whenever a purchase is made by a customer, the DBMS system will immediately deduct that number of quantity of products purchased from the online inventory so that online inventory matches with the physical quantity available in the store of the Amazon. Now we take the third example of consistency in real life. Suppose there is a birthday function of one of your near and dear, and it has been decided that you will celebrate this function in some restaurant. You know the working of the restaurant which you have chosen. You go in advance to that restaurant and ask them that you that a specified table be booked for them. It may also be possible that the restaurant you have chosen for dinner or celebration of the birthday function may be having online facility for booking of tables in that restaurant. In that case, the DBMS ensures that multiple customers are not assigned the same table. In case the restaurant is having manual system to allot the table to the customer, to a customer, it may be possible that a similar table may be booked to different customers, because one customer may approach one partner of the restaurant and another customer may approach another partner of the restaurant. So in that case conflict may arise. But in case of proper reservation system being adopted in the restaurants with the help of DBMS, this type of situation does not arise, because DBMS prevents such type of conflicts and helps in maintaining consistency in reservations. By enforcing consistency, the DBMS ensures the correctness of the database. Next, third property which we are discussing about DBMS is isolation property. Isolation property ensures that each transaction is treated as if it is the only transaction being executed on the system, and multiple transactions can execute concurrently on the database without interfering with each other. It means that though many transactions are taking place on the database at the same time, each transaction is acting as if it is the only transaction being done on the database. Each transaction must be isolated from other transaction until it is completed. Now we will try to understand this isolation property with the help of an example of an online bookstore where customers can purchase books. Suppose there is one last copy of a book which is in great demand, and the online bookseller has only one copy of the same, but the customers are many who are approaching the site. Suppose in this case only two customers A and B are approaching the site for the purchase of one particular book, which is available in single quantity. That is only one copy of that said book is available. Suppose A customer approaches the site by milliseconds ahead of B. That customer chooses the book he wants to purchase, he makes the payment, and the said book is allotted to or booked in his name. At the same time, was also trying to purchase the book, but the system, DBM system, places a lock on the transaction which is being done by A. That is, when the transaction of A completes, only then the B the transaction starts. That is, we have already learnt about the isolation levels of in DBMS. That is, read uncommitted, read committed, repeatable read, and serializable. Suppose in this case of bookseller, the isolation level used in DBMS is the highest level, that is the serializable. In that case, though A and B are simultaneously trying to purchase the same book, then the DBMS system will ensure that the transactions are to behave as if they are in serial order, that is in queue. That is, one transaction is in queue. After that, when the first transaction completes, then the second transaction starts. Now we will try to understand the situation or the example with the help of what is written. Concurrency. Customer A and B both initiate transaction to buy the last book in the inventory. These transactions are executed concurrently. Concurrently means at the same time. The DBMS system which is being used by the bookstore implies isolation levels to manage the concurrent transactions. Let us say the isolation level being used by the bookseller in its DBMS system is serializable. That is the highest level, strictest level of isolation is being used in the DBMS. We have already learnt about these four isolation levels in our previous course in detail. We have also learnt about the read lock and write lock. You can also learn about the same from our previous course. When the customer A's transaction begins, the DBMS places an exclusive lock on the book entries inventories record to prevent other transactions from modifying it. That is, when the transaction of A is going on, the DBMS system puts a lock on the inventory of the book. That is, no other person can place the order for the said book. Customer A's transaction proceeds to completion, deducting book from the inventory. When the A has purchased the book by making payment, A's transaction is complete, and when the order stands placed, the inventory which is being shown online will be deducted. That is, if there was only one book, the same will be deducted from inventory and the zero balance will be shown. Next, transaction for customer B. At the same time, customer B's transaction also starts. However, since the book's inventory record is locked by customer A's transaction, customer B's transaction temporarily held in a queue because the customer A's transaction has started slightly ahead in time, say by milliseconds. Customer B's transaction waits until the exclusive lock is released and inventory record is available for update. That is, the DBMS system will not allow the B to proceed with this transaction. When A's transaction completes and the exclusive lock which was put by A's transaction has been removed, only then the B will be able to proceed further with his transaction. This ensures, that is, this locking of the inventory record ensures that customer B does not buy the book that has already been sold to customer A. Once the lock on the inventory record is released after A's transaction completes, customer B's transaction is allowed to proceed. If the book is still available, that is, if the number of books have been say two, then one book will be available. The transaction deducts it from the inventory. B will be able to make the payment and this said quantity will be reduced from the inventory. By using isolation mechanisms, the DBMS ensures that concurrent transactions are managed effectively, avoiding scenarios where the same book or item could be sold to multiple customers due to simultaneous purchases. It means that when multiple purchases we are making on the online sites, if there was no isolation property of DBMS in force, then the situation would have arisen that the same item would have been sold to many customers. Suppose there were only 10 items which were available on the site. If the isolation property was of DBMS was not there, then it may be possible that only 10 quantity items might have been sold to say 100 customers due to simultaneous purchases. Simultaneous means concurrent transactions, as many persons will be approaching this site for purchase of say one particular item. The same product could have been sold to many customers, resulting in customer dissatisfaction because all the customers would not be able to get the same, as the quantity available with the site was only limited. It ensures a smooth and accurate online shopping experience for all users. So it ensures that the online shopping experience for customers is good. Now the next acid property of DBMS is durability. Durability ensures that once a transaction completes, the changes made by that transaction are permanently saved to the database, and these changes survive any subsequent failures such as power outages, system crashes, or system failure. It means that once you have completed your transaction, say A has purchased his book, he has made the payment, and the message has been received from the online site that particular order has been confirmed. Suppose in the meantime power goes off or internet failure occurs, internet connection fails. Even after or system crash occurs at the level of say online site. Even after that, the DBMS system has the mechanism that it will ensure that the inventory level which is being maintained at the database of the online site is properly updated. Suppose there were 100 products available, and after you're having purchased one item, 99 products would be shown on the site when the system restores, because the DBMS system ensures such type of feature because of having adopted many procedures to ensure that the correct inventory is shown even in the case of system failure, power outages, etc. Let us read what is said written here. Sometimes it happens that the transaction is incomplete at the time of failure, and the changes made by these incomplete transactions have not been committed. Committed means saved to the database. It means that transaction is suppose going on. There are many operations which have to be performed in the transaction. when the transaction is still not complete and the power goes off or system crashes occur. So when the transaction is incomplete and all the changes have not been committed to the database, committed means changes have not been recorded in the database, then the system will ensure, DBMS will ensure that all the transaction is rolled back to the original situation. So all the changes made by the incomplete transaction will be reverted and will not affect the state of the database system, that the database system will be restored in its original position. For example, imagine you are using an e-commerce platform to place an order for a product. When you finalize the order, a transaction is created in the database to reduce the product's stock quantity and record your purchase. It means that when you have placed the order, you have made the payment. Payment has been made by you, order has been booked, and in the meantime, power goes off at the level of online site. When you have purchased the item, then the DBMS system has to ensure that the quantity purchased by you has to be reduced from the inventory of the online site. So when the inventory was to be updated, the power goes off or sudden server crash occurs. If there was no DBMS property of durability, that is, there was no asset property of durability in DBMS, it would have been possible that the order was confirmed to the client and on at the same time inventory level might not have been reduced. Without the durability property, there is a risk that the stock reduction might not be saved due to the crash or power failure. This could lead to issues such as overselling products and disappointing customers. Now, the durability property comes in action. Thanks to the durability property of DBMS, when the system is restored after the crash, it ensures that the stock quantity has indeed been reduced as per your order, even though there was a momentary interruption during the order processing. The database maintains the accurate stock level, preventing potential stock related problems. The example given above demonstrates that durability is an important feature of DBMS, which ensures data accuracy and system reliability, particularly in cases of e-commerce where product availability and inventory management are important. Because in the e-commerce, if there is mis-selling or selling of a product which is not available actually in physically in the inventory or the stock of the online site, it will result into large scale customer dissatisfaction. So here the durability property of DBMS comes into play and ensures that such type of situations do not arise. Now, how the DBMS system ensures durability? That is, when the failure of the power or system crash has occurred, though the order has been confirmed to the client, how the system ensures that the inventory level is updated even after crashing of the system or power failure. Some of the techniques used by the DBMS to ensure durability are write ahead logging, redo logs, and transaction journaling. These techniques collectively contribute to the durability property of DBMS. That is, these techniques collectively play a role to ensure that this system properly shows the accurate items and that the committed changes are reliably preserved even in the face of unexpected system disruptions. In conclusion, we can say that these acid properties of DBMS are very important for ensuring data consistency, integrity, and reliability in databases. Atomicity guarantees the all or nothing execution of transactions, that is all or none. Consistency ensures the database transitions from one valid state to another. Isolation lab prevents interference between concurrent or simultaneous transactions, and durability property safeguards data changes against system failure. These properties collectively make DBMS a reliable and efficient tool for managing data in modern organizations, where the organizations have to deal with structured data, semi-structured data, object-oriented data, graph data, etc. Thanks for watching. If you like our course, please spare some time to give a star rating to our course.